might have enjoyed a ride in the giant wheel. The acceleration of a giant wheel is non-uniform. It varies as the wheel goes upward against the gravity and as it comes down in the direction of gravity. Motion of a giant wheel is an example of motion in the vertical circle. Let us understand the physics behind a giant wheel. Here you can see that a boy is trying to rotate a ball tied to an inextensible string in the vertical circle. Initially, he provides a small force to the ball. You can observe that the ball comes down after attaining a certain distance. When he increases the force slightly, the ball covers a greater height and then falls back. When he goes on increasing the force, a stage comes when the ball goes to the maximum height and moves in a circular path. The path of the object in the vertical plane is a circle. Let O be the center of the circular path of the object and let L be the length of the string. The length of the string will be the radius of the circle. Let M be the mass of the object. Now, we will divide the motion of the object in two parts. When it goes up in a direction opposite to that of the gravity. When it comes down in a direction same as that of the gravity. When the object goes up in a direction opposite to that of the gravity. The speed of the object goes on decreasing as it goes upward. The angular displacement goes on increasing. At highest point, the speed of the object becomes minimum and angular displacement becomes maximum. When the object comes down in a direction same as that of the gravity. After attaining the highest point, the object starts moving downward. Its speed goes on increasing and angular displacement goes on decreasing. When object comes back at its initial point, its speed becomes maximum and angular displacement becomes zero. To understand this motion, let us assume the velocity of the object at lowest point A be VA and velocity at the highest point B be VB. Let at a particular point P, its angular displacement be theta, and let velocity at this point be V. The direction of velocity at P will be tangentially outward. The forces acting on the object at point P are the weight mg of the object acting vertically downward and the tension T in the string directed towards the center of the circle. We can resolve the weight into two components, that is, the tangential component mg sin theta and radial component mg cos theta. The net radial force acting on the object will be T minus mg cos theta. This net force will provide the required centripetal force to keep the object in circular motion. The expression for the centripetal force is shown here. Thus, for a given mass and radius, the velocity of the object at a point depends on the angular displacement. At point B, the velocity becomes minimum and tension in the wire becomes zero. Therefore, V is equal to under root Lg. Thus, the minimum speed required to keep the object in motion in the vertical circle depends on the radius of the circle and is equal to under root Lg. Similarly, the velocity at point A is given as V is equal to under root 5 Lg. This is the reason why the object falls down without moving in a circle when we move it with a speed less than the minimum speed. Daily life examples. You might have experienced that when we move a bucket filled with water in vertical circle with a certain speed, the water doesn't fall down even when bucket is upside down. This is because with a speed greater than the minimum speed, the water along with the bucket keeps on moving in the circular path and hence doesn't fall down. You might have seen a person riding his motorcycle in vertical circle inside the circle of death in a circus. Here also, the necessary condition to keep the motorcycle in the vertical circle is that the speed at the highest point should be equal to or greater than under root Lg, and that at the lowest point should be more than under root 5 Lg. For this very reason, the motorcyclist first acquires a velocity greater than under root 5 Lg and then only starts moving in the vertical circle.